Pilots use the primary and secondary flight control surfaces to move the airplane in flight. The primary flight controls are the ailerons, the elevators, and the rudder. The secondary flight controls are the spoilers and the high lift devices. The spoiler speed brake system is made up of flight and ground spoilers. The flight spoilers can move to aid the ailerons with roll control, or they can be used to slow the airplane. After landing, the ground spoilers deploy with the flight spoilers to slow the airplane. High lift devices increase the wing area and change the shape to increase lift at low air speeds. These devices include two leading edge flaps located inboard of each engine, four leading edge slats located outboard of each engine, and inboard and outboard double slotted flaps on the trailing edge of each wing. Flap positions 1 through 15 supply increased lift with only a small change in drag. Flap positions more than 15 supply increased lift and drag to permit slower approach speeds and better airplane control. The primary flight controls are supplied power by these hydraulic systems, and the secondary flight controls are powered by these. The ailerons are the primary surfaces for roll control. The flight spoilers assist the ailerons. Roll commands come from the control wheels and the autopilot. The control wheels are connected to each other and then connected by cables to the aileron power control units, or PCUs. Hydraulic systems A and B supply power to the aileron PCUs and the flight spoiler PCUs. The flight control panel is on the overhead panel. The flight control switches are usually in the guard closed on position, which lets the related hydraulic system supply power to the flight control system. The spoiler switches are for maintenance personnel to do system tests. Controls for the aileron trim system are at the aft end of the aisle stand. The aileron trim indicators are on the top of the control columns. The aileron trim switches send an electrical signal to the feel and centering mechanism to set new aileron and control wheel positions. The trim switches must move together for the system to work. When the autopilot is engaged, the autopilot roll channel moves a cable to the feel and centering mechanism, which in turn moves a cable to the aileron PCUs. The four flight spoilers help the ailerons to roll the airplane. The spoilers are hydraulically operated. The flight spoilers start to move after more than 10 degrees of control wheel movement. In a turn, the spoilers come up to kill lift on the wing with the up aileron and stay down on the wing with the down aileron. Now let's look at some non-normal situations. If you experience jammed ailerons or spoilers, the transfer mechanism allows you to roll the airplane. If the ailerons jam, force applied to the first officer's control wheel operates the spoilers to roll the airplane. The captain's control wheel does not move. If the spoiler system jams, force applied to the captain's control wheel operates the aileron to roll the airplane. The first officer's control wheel does not move. If all hydraulic pressure to the ailerons is lost, the pilots can manually control the ailerons, but greater force is required because of cable friction and air pressure loads. The elevators are the primary flight controls used to change the airplane pitch attitude. The stabilizer assists the elevators. The elevator is moved by the control columns, autopilot, and Mach trim system. The control columns are connected to each other by the transfer mechanism, which allows elevator control if a part of the elevator system jams, and to cable systems, which connects the control columns to the elevator PCUs. The PCUs use hydraulic system A and B pressure to move the elevators. An engaged autopilot sends a signal by cable to the elevator feel and centering unit. This signal is added to stabilizer position, hydraulic pressure, and pedostatic inputs in the elevator field computer to tell the elevator how much to move. The elevator feel and centering unit supplies artificial control feel to the pilots through the control column. As swept-wing airplanes, like the 737, increase airspeed toward Mach 1, they start to pitch down because of the aerodynamic forces on the airplane. The Mach trim system is automatic at speeds above Mach 0.615. The air data part of the ADIRUs sees airspeed and sends a signal to the FCCs. The FCCs send a command to the Mach trim actuator, and the actuator tells the feel and centering unit to make an elevator adjustment. The airplane pitch attitude also changes if these components send a command to the horizontal stabilizer. Cables transmit manual commands from the pilot's stabilizer trim wheels to the stabilizer. The two control wheel trim switches send electrical signals to the two-speed main electric portion of the trim motor to move the stabilizer. These switches must be moved together. With the flaps extended, the trim moves faster than with flaps up. The engaged autopilot commands changes to the stabilizer with signals to the autopilot portion of the trim motor. Movement of the stabilizer trim switches disconnects the engaged autopilot. Most controls and indicators for the stabilizer trim system are on the control stand. The stabilizer trim indicators point to the units of stabilizer trim, and the green bands show the approved takeoff trim range. An intermittent horn sounds if you try to take off when the stabilizer trim is not in the takeoff range. An automatic speed trim system adjusts trim to improve manual flight characteristics. The system operates when the autopilot is disengaged and there are airplane conditions of low gross weight, aft center of gravity, and high thrust. The system most frequently operates during low speed, high thrust conditions such as takeoff or go-around. Speed trim sends a signal through the autopilot trim system to move the stabilizer. When you engage the autopilot or make a stabilizer trim input, speed trim stops. Now let's look at some non-normal indications. When the field differential pressure light and the lights that follow come on, they cause the master caution and annunciators to also come on. This light illuminates when the elevator field computer senses a significant hydraulic pressure difference between hydraulic system A and B and the flaps are up. The field system will operate with only one hydraulic system. This condition does not require crew action in flight. An air pressure differential caused by a blocked pitot tube will also cause the field differential pressure, master caution, and flight control's annunciator lights to come on. The speed trim fail light illumination tells us of a dual-channel speed trim failure in the flight control computer. A single-channel speed trim failure makes the master caution light and the flight control annunciator come on when the master caution system recall is activated. No crew action is required in flight for a single or dual failure. The Mach trim fail light and master caution lights illuminate if there is a dual-channel Mach trim system failure. A single-channel Mach trim failure makes the master caution light and the flight control annunciator come on when the master caution system recall is activated. The crew must limit airspeed to 280 knots or 0.82 Mach. The stab out of trim light can illuminate for a moment if the autopilot requires a large trim change and the stabilizer is not in the correct position. When the stab out of trim light illuminates for a longer time, a malfunction has occurred. This could require you to hold the control wheel, disconnect the autopilot, and trim the stabilizer. If you move the control column opposite to the trim system, or the control column is moved out of the usual range, a cutout switch stops all stabilizer trim operation. When stabilizer trim is stopped out of range, move the stabilizer trim override switch to override. This permits stabilizer trim operation. The rudder controls yaw, the movement around the airplane's vertical axis. The one-piece rudder is attached to the vertical stabilizer. With hydraulic power, you can move the rudder through the rudder pedals or the rudder trim system. Automatic inputs to the rudder come from the main yaw damper during normal operations, or from the standby yaw damper during manual reversion flight. The yaw damper operations are controlled through two stall management yaw damper or SMYD computers. Rudder pedal inputs move cables to the feel and centering unit and the main and standby rudder PCUs. The feel and centering unit sets the rudder pedal position and feel. The main rudder PCU consists of two independent input rods, two individual control valves, and two separate actuators, one for the hydraulic system A and one for hydraulic system B to move the rudder. The standby rudder PCU is controlled by a separate input rod and control valve and powered by the standby hydraulic system, which is provided as a backup if System A and/or System B pressure is lost. Either PCU can supply rudder control. Each input rod has an individual jam override mechanism that allows input commands to continue to be transferred to the remaining free input rods if an input rod is hindered or jammed. The main rudder PCU contains a force fight monitor, FFM, that detects opposing pressure force fight between A and B actuators. The FFM output is used to automatically turn on the standby hydraulic pump, pressurizing the standby PCU. The rudder trim system can move the rudder to remove unwanted forces from the rudder pedals. Rudder trim inputs change the feel and centering unit neutral point. This makes the rudder pedals and the rudder move. The rudder trim control and indicator are on the aft electronic panel. You can turn the rudder trim control to the left or right to change rudder trim. The indicator shows the rudder's trimmed position. This flag is in view if electrical power to the trim indicator is lost. The yaw damper prevents Dutch roll. It also helps with turn coordination and gust damping. Yaw damper electronics are in the two stall management yaw damper computers. The left SMYD computer supplies yaw damper inputs to the main rudder PCU to tell how much to move the rudder. The right SMYD computer supplies turn coordination, gust damping, and Dutch roll prevention through the standby yaw damper. The ADIRUs send speed and yaw rate data to the stall management yaw damper computers. ADIRU data is added to control wheel inputs and sent through the yaw damper to tell the PCUs how much to move the rudder. The yaw damper indicator shows the inputs to the rudder, but the rudder pedals do not move. Standby yaw damper inputs to the rudder are not shown on the yaw damper indicator. Pilots can override either main yaw damper or standby yaw damper inputs with the rudder pedals or rudder trim. Now let's look at some non-normal situations. The yaw damper light comes on when the yaw damper disengages. If it is a momentary problem, the yaw damper may reset when the switch is moved from off to on. The main yaw damper does not operate if hydraulic system B is not available. In this condition, the yaw damper switch stays at on and the yaw damper light does not illuminate. Move the System B flight control switch to standby rudder. The yaw damper switch moves to off and the yaw damper light illuminates. The yaw damper cannot be engaged when only System B is inoperative. If hydraulic pressure from systems A and B is not available, the rudder must be operated by the standby hydraulic system. Move the flight control switches to standby rudder. This starts the standby hydraulic system, which supplies power to the standby rudder PCU. Note that the standby rudder on light illuminates anytime the standby rudder hydraulic system is pressurized. Standby rudder on light illumination activates the master caution and flight control lights on the system annunciations panel. Move the yaw damper switch to on. Yaw damper protection is now available through the standby yaw damper. During standby yaw damper operation, movement of the control wheel sends a signal to the standby rudder PCU to move the rudder. This gives rudder assist to coordinate the airplane in turns when control of the ailerons is through manual reversion. If a rudder cable fails in flight, use the rudder trim to make rudder inputs. If the rudder pedals jam, normal rudder and nose wheel steering inputs are not possible. Rudder trim is also not available. If you think ice caused the jam, descend when possible to warmer air.